In this problem, we have a girl that's operating a radio-controlled model car on a smooth, flat cement playground area. The girl stands at the origin of an XY coordinate system, and the surface of the cement lies in the XY plane. The car's position is given by R, which has an X direction and a Y direction. The X and Y component velocities are given by x dot equals 2 plus 3t squared meters per second, and y dot equals 6 plus 0.5 t cubed meters per second. At a time of t equals 0, the car is located at x equals 2 meters and y equals 6 meters. All right, we want to determine a bunch of things. First, we want to determine, as a function of time, the position, velocity, and acceleration of the car. Then we want to plot the position of the car between 0 and 2 seconds. We want to find the displacement for the same time period, determine the velocity and acceleration at 1 second, and the average velocity and acceleration between 0 and 2 seconds. All right, so we know that this is the general equation for position. We know the x and y component velocities, and we know some initial conditions. All right, and this is what we want to find. All right, so what we want to do for this problem is we know the velocity is a function of time. So we want to get the position. We'll get the position by integrating, and we'll get the position as a function of time because we want to do a lot with that equation. And then we can take the velocity, take the derivative, and find the acceleration as a function of time. It's always good to get these equations as a function of time so that you can do things with them. All right, once we know the position, velocity, acceleration as a function of time, we can plot them, do anything we want with them. All right, so let's start with the position. All right, we have a general equation that the velocity equals the position over the derivative of position over time. We can rearrange that because we're going backwards. We want to go from velocity to position. So we're going to integrate that. And furthermore, we can take this vector equation and break it up into the two components. So we can break it up into the x component and the y component. Just makes it easier. All right, let's start with the x direction. So we put the x component velocity in on the velocity side, integrate it. Now remember, they gave us initial conditions. So at time t equals 0, the position in the x was 2. And then we're going to integrate to variables. So the upper limit's just going to be variables. It makes the equation much more useful. All right, so we do the integration, rearrange the equation, and we get the position in the x as a function of time. All right, the y direction, we do it a similar way. We put the y direction velocity in. Remember the initial conditions at time t equals 0, the y position is 6, and then variables up at the top. We integrate, get the y position as a function of time, and then we can get the overall position, which has an x component and a y component, and there we go. So we have the first part done. Once we have the position, we can determine different points. So for example, at time t equals 0, we know the initial position is 2 and 6. Well, let's plug in 0.5 seconds. Well, we get 3.125 and almost 9. And we do that for 1 second, 1.5 seconds, and 2 seconds. And this allows us to plot the position on the xy plane. So at time t equals 0, we have 2 and 6. At time 0.5, we have about 3.125 and 9. So we plot it there, and we go on and we get this red curve. So this is how the car is going to move along the cement. All right, the problem also asked us to find the displacement, which is the position at 2 seconds minus the position at 0 seconds. Well, we have that, right? We already calculated it and put it in this table. So we just plug it in, and we get that the displacement is 12I plus 14J, which makes sense, right? So if you count the squares and go over in the X, that's 12. If you count the squares and go up in the Y, that's 14. All right, so next, velocity. Velocity was given in the problem, so it's not a big deal. We just write the velocity equation, plug in 1 second, get that, find the average velocity, which is displacement over change in time. We know the displacement, so we get the average velocity. Then we can get acceleration. So acceleration is the time rate of change of velocity. We're given the velocity equation, we just take the derivative of it, and we get the acceleration. We can plug in 1 second, get the acceleration at 1 second, and find the average acceleration, which is the change in velocity over change in time. So change in velocity is the velocity at 2 seconds minus the velocity at 0 seconds. No problem, we already have the velocity equation, so we can get those values divided by the 2 seconds and get the average velocity or average acceleration. All right, the problem also asked us to plot it. So for the velocity, this is 1 second right here, and we want to go 6 in the I and 7 in the J. Now, if you do that, you get a velocity that's at this angle, right? And notice that the velocity is tangent to the curve. That's important, right? If we got a velocity that was not tangent to the curve, we would know we did something wrong, because velocity is always tangent to the path curve. We can plot the acceleration as well, so 6 in the X and 1.5 in the J, so we have a shallower angle here. And the acceleration, it's usually not tangent to the curve, so this is fine. And that's it. We calculated everything we need to know.